In Lab 4, we will be comparing the observed and model motion of a mass moving in an arc while oscillating on a spring. Through this, we will also examine the changing kinetic and potential energies of the system. We observed the moving mass using Tracker and set up a model using observed values for properties of the system using VPython. The model was able to predict the observed motion, and it was found that the changes in energies of the system followed distinct oscillation patterns corresponding with the motion. Changes in potential energy of gravity and the spring were always opposite in sign. Changes in kinetic energy oscillated twice as fast as the changes in potential energies, and the change in total energy was always zero. Motion of the oscillating mass was first observed in Tracker. Information needed to create the model of the motion, including the relaxed length of the spring and the spring constant, was calculated from observations of the mass using a form of Hooke's law, which states the force of the spring is proportional to the stretch of the spring. Using Tracker, I estimated the length of the oscillation periods for the x and y positions. The x oscillation period was estimated to be 1.65 seconds, and the y oscillation period was estimated to be 1.45 seconds. Looking at the graphs, we can see the oscillations do not line up exactly, with the x position going through about 5.5 oscillations, while the y position goes through about 6 oscillations. This can be explained by the magnitude of the distance traveled in the x and y direction being different, and that the mass begins at the top of the oscillation curve for y and the bottom of the oscillation curve for x. The model in VPython was created with a loop which would update the gravitational and spring forces on the mass and calculate Fnet, then use Newton's second law to update the ball velocity and position, update the spring position to allow the spring force to be calculated on the next step, and finally calculate values for the kinetic energy, potential gravitational energy, potential spring energy, and the change in each energy. The visual model created was compared to the observed motion. The visual model shows the predicted mass location as a blue ball with a blue path, and the observed mass location as a red ball. The graph shows the y position versus time points for the observed mass in red and for the predicted mass in blue. The observed position is best predicted by the model during the first oscillation from 0 to about 1.6 seconds and gradually becomes more inaccurate at the beginning of each oscillation as time passes. This discrepancy may be due to energy dissipating from the observed system due to drag force, which is not accounted for in the model predictions, and error in observing the exact center of mass during each step in Tracker. Despite this, it is still a fairly accurate prediction. Energy during the motion was observed. The visual model shows the gravitational potential energy with the black arrow and the spring potential energy with the blue arrow. Notice that the potential gravitational force always points in the negative y direction, while the potential spring force always points toward the spring origin. We can also observe that as the mass moves in the positive y direction and the spring contracts, gravitational potential energy increases and spring potential energy decreases. The opposite occurs as the mass moves in the negative y direction and the spring expands. Energy changes over time were graphed. Change in kinetic energy is shown in blue, change in spring potential energy is in red, change in gravitational potential energy is in green, and the total energy change is shown in yellow. We can see all of the energy changes, aside from total energy, oscillate in a constant pattern. The kinetic energy is seen to oscillate twice as quickly as the potential energies, completing 2 cycles in the potential energies 1. The changes in gravitational potential energy and spring potential energy are always the opposite sign, which is consistent with our observations of our visual model. The total change in energy is always 0, which is expected as this is assumed to be a closed system with no energy escaping to the outside. Since the total change in energy of the system is 0, the conservation of energy principle is satisfied, which is the total energy of an isolated system remains constant regardless of energy changes within the system.